4.5, limits at infinity. By the end of this section, you should be able to determine finite limits at infinity, determine the horizontal asymptotes, if any, of the graph of function, and determine infinite limits at infinity. So limits at infinity, what does it mean? So it means, let's look at one example here. This is the graph of 1 over x. This is the name of the function. When x approaches to positive infinity here, this graph is approaching to 0. And when x approaches to negative infinity this side, this graph is again approaching to 0. So that's called limit at infinity. The end behavior of the graph is called limit at infinity. What happens when x is very, very, very high? That's the limits at infinity. So let's look at another example. This is the graph of function 3x squared over x squared plus 1. You can plot this graph by using some graphing utilities, graphing calculator, or just use some online tool. And as you can see here, this is the bound, upper bound of this graph. This graph never crosses or touches this bound. Okay, what does it mean? It means when x approaches to infinity, the graph is approaching to this line, y equal to 3. And when x approaches to negative infinity, that side, the graph is approaching to, again, that very same line, y equal to 3. We can verify this thing by using table. Let's pick some values, 0, 1, 10, 100, and so on, so on. As you go, to the right side, very, very high number, the value of the function approaches to positive 3. You can calculate this value by using the function you have given, which is 3x squared over x plus 1, I guess, x squared plus 1. So put the value x equal to 0, x equal 1, x equal 10, x equal 100, and keep growing. As you grow, the function value never crosses 3. It will be always less than 3. Same thing happens if you go to the left side. As you go to the extreme left, the function value never crosses 3 or touches 3. So 3 is the upper bound for this function. So how do we write this thing? And what is this called? These values, when x approaches to negative infinity or positive infinity of the function, these values are called limits at infinity. And this is the notation we use. Limit x approaches to negative infinity of the function f of x is 3. Similarly, limit of the function f of x when x approaches to infinity is positive 3. Both of these limits are, finite limits. So there is a proper definition of the limits we define in chapter 2. The very same way we can define a limit at infinity. Let L be a real number. Then L is called limit of the function f of x when x approaches to infinity. If for each positive epsilon there exists an positive number m such that the difference between this function f of x and L is always less than epsilon whenever x is greater than m. This is the proper way to define the limit. This is the very same definition we use in chapter 2. So as x approaches to infinity or x approaches to negative infinity, if the limit, the value of the function approaches to L, that's called the limit of the function, and this is the proper way to define that function. This is the proper way to define the limits. Okay, what does it mean actually? It means, let's think about that number we are using, x is greater than m. So for any epsilon, no matter what epsilon value you choose, you should be able to find this m such that for anything towards the right of this m, the value of the function and this L, the difference between them should be always within this epsilon boundary, epsilon limit, So the difference between the L and the value of the function, if you pick anything x greater than m, should be inside this boundary. So that's the meaning of limits at infinity. So why we're talking about the limits at infinity? Because these limits would help us to plot the graph by finding the horizontal asymptotes whenever it's possible. So how do you define the horizontal asymptote? Horizontal asymptote is actually a line y equal L. Whenever you try to find the limit of the function f of x when x approaches to negative infinity or positive infinity, If those limits is either of this limit is L, then y equal to L is called the horizontal asymptote for that function, for that graph of the function. Okay, so the properties, if you remember the limit property we discussed in chapter 2, the same thing applies here for the limit at infinity, but make sure that the limit should be finite. So we can apply the this limit to the sum of the function if the limit of these two functions exist. And similarly, we can apply this limit to the product of the function. And similar thing holds when you take the limit at negative infinity. And there is a theorem. It's very, very useful theorem. Just remember this, conclusion of this theorem. If R is a positive rational number, and C is any real number, then limit of this expression constant over x to the power r when x approaches to infinity or negative infinity, it's always equal to 0. You remember the example I gave you, limit of this function when x approaches to infinity, because the power of this x is 1, is 0. Similarly, x approaches to negative infinity, it's 0 because of this theorem. So if you try to find the limit of exponential function e to the power x when x approaches to negative infinity, it would be 0. And when x approaches to positive infinity, it would be 0 as well. So if you remember the graph of e to the power x, this is the graph of e to the power x. So when x approaches to negative infinity on this graph, you can see that the graph is approaching towards 0. And then similarly, this is the graph of e to the power negative x. When x approaches to positive infinity, this graph is approaching to this x-axis, which is y equal to 0. So these are the results you should keep in mind because they are very helpful. For example, let's say if you would like to find the limit of this expression here, 5 minus 2 over x squared, because the limit of the 5 when x approaches to infinity is 5 itself, and limit of 2 over x squared can be calculated by using this theorem results, which is 0. So finally, the limit of this expression is 5. The limit of this 3 over e to the power x when x approaches to infinity, this expression goes to infinity. As you can see here, this is the graph of e to the power x. When x approaches to infinity, this graph goes to infinity, but 1 over e to the power x goes to 0. So that means the limit of this expression is 0. Okay. When we try to find the limit of this kind of rational expression, look at here. When you apply x approaches to infinity on the top and x approaches to infinity on the bottom, it gives you infinity over infinity form, which is called indeterminate form, and we don't know how to find the limit of that type of the form as is. So first of all, for finding the limit of this kind of expression, indeterminate form, we need to simplify this problem. So factor out x on the top, factor out x on the bottom, and then after that just simplify, and after that you can see that 1 over x goes to 0 when x approaches to infinity, and that helps us to find the limit of this expression is equal to 2. This y equal to 2 line is called horizontal asymptote for this rational function according to the definition of horizontal asymptote. So if you try to plot the graph of this rational expression, use graphing calculator or just online tool, and you will be able to see that the graph of this function, as you can see here, y equal to 2, that's your horizontal asymptote. And again, we know the x equal to -1 is the vertical asymptote. So these horizontal asymptotes and vertical asymptote, they would be very, very helpful while plotting the graph. Okay, so there are some guidelines for finding the limits at positive infinity or negative infinity of rational function, which is also called finding the horizontal asymptote whenever it's possible. Let's say you have a rational function r of x, which is there is a polynomial on the top, there is a polynomial on the bottom, something like this, like this, 2x minus 1 over x plus 1. So there is a polynomial on the top, there is a polynomial on the bottom. So first of all, if the degree of the numerator, which is the top one, is less than the degree of the denominator, then the limit of the rational function is 0. Here the degree on the top is 1, the degree on the bottom is 1, so that's not the point we can apply here. But if you go to the number 2, if the degree of the numerator is equal to the degree of the denominator, then the limit of the rational function is the ratio of the leading coefficient. So what is the limit of this rational function when x approaches to infinity? It's a ratio of the leading coefficient here, that the leading coefficient on the top is 2 and on the bottom is 1. 1 is the number in front of x. There is nothing, that's why we can write 1. So what is the limit of this function? It's a y equal to 2. That's why y equal to 2 is a horizontal asymptote for this function. There is another situation as well. If the degree of the numerator is greater than the degree of the denominator, then the limit of the rational function does not exist. We cannot find the limit when x approaches to positive infinity or negative infinity. In that case, we cannot find the horizontal asymptote. I'm going to give you one example here. Some examples. Horizontal asymptote. Look at the function 1 over x squared plus 1 when x approaches to infinity. Because of this guidelines, number 2, if the degree of the numerator is equal to the degree of, number 1, if the degree of the numerator is less than the degree of the denominator, then the limit of the rational function is 0. So as you can see here, the degree on the bottom is 2, degree on the top is 0, because this is a constant function. That's why y equal to 0 is a horizontal asymptote. Y equal to 0 means actually this is the x-axis. That's the y equal to 0. So when x, the function approaches the same horizontal asymptote to the right and to the left side. This is always true of the rational function. Functions that are not rational, however, may approach the different horizontal asymptote to the right and to the left. So if you are talking about the rational function, then they approach to the same horizontal asymptote. One more example here, 1 over 1 plus e to the power negative x. This is not a rational function. When x approaches to infinity, as you can see here, when x approaches to infinity or negative infinity, the value of e to the power negative x, as you can see here, when x approaches to positive infinity, e to the power negative x goes to 0. So the line, the graph approaches to this line y equal to 1. So limit when x approaches to negative infinity, this function here, it approaches to infinity, and 1 over infinity approaches to 0. That's why this graph approaches to y equal to 0. So there are two different horizontal asymptotes here, y equal to 0 and then y equal to 1. We can verify that by looking at this table as well. Just plug the value of x when x is when you choose x greater or bigger and bigger, the value of the function, it cannot be greater than 1. It's always less than 1. And when x is less than a very small and a small number, the function approaches to 0. So that's the reason the horizontal asymptote y equal to 1 and y equal to 0 are two horizontal asymptotes for this function. Okay, next topic is infinite limits at infinity. So up to this point, we found finite limit at infinity, but now we're going to talk about infinite limits at infinity. So the very same way we use the proper definition of the limit, we're going to repeat the very same thing. A limit of the function when x approaches to infinity is called infinity if for each positive number m, there is a corresponding number n such that the value of the function is greater than m whenever x is greater than n. Okay, very same proper definition we used for the we use in the chapter 2. We can apply the same thing here. So the summary is, whenever you try to find out the limit of the function when x approaches to infinity or negative infinity, if the limit is infinity or negative infinity, that's called infinite limit. Example, look at here, x cube, when x approaches to infinity, x cube approaches to infinity, because x cube is keep growing, so there is no bound. If you look at the graph of x cube, the graph of x cube would look like this. So when x approaches to infinity, as you can see here, the graph is keep going up and up, and when x approaches to negative infinity, the graph is keep going down and down. That's why the limits are infinity and negative infinity. So that's the graphical illustration. You can use a graphical tool, or just use a tool you can find online. Okay, so that's the limit at infinity. Infinite limit at infinity.